Hi there, this is Cameron Ogden with Datum. Welcome back to part 2 in our series, An Easy Introduction to Artificial Intelligence, Machine Learning, and Deep Learning. So in this video, we're going to go a layer deeper and show you how machine learning and deep learning work. We'll also introduce you to a few terms you might hear in the world of machine learning, just so you're familiar with some of the concepts. If you watched part 1, you'll remember that machine learning is a subfield of artificial intelligence, and deep learning is one form of machine learning. The thing that makes machine learning unique overall is the algorithms actually learn from experience, which is to say they learn from data. Let's start with an analogy to explain how this works. Suppose you and your friend are playing darts and someone bets you that you can't hit the bullseye while wearing a blindfold. How would you do it? You would throw a dart, your friend would see how far you missed, they would tell you how to correct your throw the next time, and then you would throw again. Assuming you were good at following instructions, like machines, you would probably get closer to the bullseye on each throw. And if you were to repeat that cycle over and over again, throwing a dart, having your friend see how far you missed, and then coaching you on your next throw, you could get really close to the target even though you can't actually see where it is. This is very similar to how machines learn. The first step is making a prediction or a hypothesis. The second step is to understand how far off the guess was from the target or the error. And then the last step is to learn by making adjustments before the next prediction is made. So let's use a machine learning example to help this sink in. What if we were in the shoe business and we wanted to predict how much money our next shoe would make? One way to approach this is to look at other shoes that have common features to our new shoe and then analyze the historical data of the sales performance of those other shoes that have common features. So those common features might be things like the number of retail stores that carry those shoes, the number of weeks promoting the shoe prior to its release, the month of the release itself for seasonality, and so on. For example, let's take a look at one feature, like the number of stores that might carry our shoe. Taking our one feature for the number of stores carrying similar shoes, we could probably find data that might look like this, with the name of the shoe, the number of stores that carried that shoe, and the total revenue those shoes made. And if we were to plot the data on a chart, it might look something like this. One of the most popular models used in machine learning to predict an outcome is called linear regression, which basically means finding a straight line that best fits these data points. Here's how we do it. Just like our dartboard example, the first step is to make a prediction, which in the machine learning world is called a hypothesis function. Our first prediction might be something like this red line. One data governance call out here, the starting point will determine our first outcome. If the efficacy of the data is high, then our first guess is better, which means we'll be closer to our target and the learning process will be much more efficient. The second step in training the model is to identify how far our guess was off. In other words, the error. And if we were to add all of these errors together and average the distance, then we would know how far our first guess was off from our target. Remember, we're calculating these errors on the historical data of shoes that have similar features. The reason is if we can train our machine on past historical data of shoes that we already have the revenue totals for, then we can apply that prediction model to our new shoe and get a close idea of how it will perform based on the historical data. Now for the third step. Our algorithm learns from the error, adjusts the model, and gets ready to make a new prediction. We won't get into the calculus here, but this learning step is called function estimation. And this is the point when the machine applies new weights based on the errors from the previous step, and then prepares to make a new prediction. Just like how we might aim our dart a little to the right on our next throw if we miss the board to the left. So with the weight adjustments and new guesses made, like this orange line here, which is a little bit better than our previous prediction, the errors get calculated and the algorithm gets adjusted again. And this continues to happen over and over again until eventually the line finds the best fit among our historical data points. This recurring process of reducing the errors and getting closer to our goal is called gradient descent, and it's one of the most well understood methods in all of machine learning. Finally, now that we have a line that best fits our historical data points, we can make a prediction by plugging in the number of stores that might carry our shoe. So if our new shoe will be released in 2,000 stores, we can see that the intersection of 2,000 stores amounts to a prediction of about $1 billion in sales. And if we were to carry the shoe in 1,600 stores, then we could expect to sell roughly 800 million in shoes, and so on. So again, this model of finding the best fitting line is called linear regression, and the method used to minimize the error in a prediction is called gradient descent. For simplicity's sake, we made our prediction on just a single feature based on the number of stores selling the shoe. But you should know in the machine learning world, algorithms are typically modeled off of hundreds or even thousands of features to arrive at a prediction. Because of the magnitude, governance plays a prominent role in securing the features and the data used in the algorithm. Now you might be thinking, what if I don't have historical data? Or what if it's not labeled where it's clear to see previous trends and patterns? Working with unlabeled data is a different type of machine learning called unsupervised learning, whereas working with labeled data is referred to as supervised learning. To keep things simple in this video, we're using supervised learning examples because, number one, they're easier to understand, but number two, they're also much more common and applicable to the machine learning goals that most companies have in the real world. We would have to cover unsupervised learning methods in a separate discussion all to itself. So that's one example of how machine learning works. Let's shift over to deep learning. If you remember from part one, deep learning is modeled after how the human brain thinks by using artificial neural networks to recognize patterns in text, images, videos, audio files, really almost any kind of data. We'll see how these neural nets are made up of individual neurons, which each play a role in helping the overall deep learning network work. Let's take a look at an example. Suppose we're a healthcare provider and we want to predict whether a patient is at risk for a chronic illness so we can provide better advanced treatment and medicine. Here's a patient data set, and we can see the features on the top row, and we can also see previous patients which have been diagnosed with a chronic illness. Given these features and results, we can use our neural net to figure out what common patterns might exist in chronically ill patients. In doing so, we can then better understand the qualities that future patients might have that contribute to a higher risk of illness. To start our neural network, we need to input the features from our data set, things like age, whether the patient is a smoker, their body weight, etc., and guessing how much weight those features should have in determining whether a patient has a high risk for a chronic illness. Just like in the machine learning example, the weights are just a prediction to start. These features and weights are then fed into a prediction where a decision is made whether the patient is at high risk. What we see here is an example of a neuron that is the building block for our neural network. Using just a single neuron only works for simple problems where the result has a linear relationship to the output. For example, age is a feature that becomes more important of a factor the older a person gets. So a patient that is in their 30s or 40s might visit a doctor 1 or 2 times a year. But a patient in their 70s or 80s might go far more frequently. So how can we capture this kind of complexity in our model? Remember that neural networks are modeled after the human brain. And our brains don't rely on just one neuron. We use many neurons that each play a role in how a larger decision is made. So to be more clever, we could run this algorithm multiple times with different weights that each capture different edge cases. Having the ability to apply different weights allows for us to model functions that are too complicated to be modeled by just one single neuron. Now, we have 4 different outcomes as determined by our individual neurons, each that were calculated using different weights. We can stack these decisions together into what is called, in deep learning terms, a hidden layer. Let's combine the results in this hidden layer into one final prediction, which is called the output layer. We'll run them through the same algorithm again, and we'll use a final set of weights between our hidden layer and the output layer. This will combine the estimates from our 4 different neurons to make a master prediction. So I know there's a lot going on here, but just remember the basics. We're feeding data into our neural network. We're using individual neurons to each make their own calculations based on unique weights, which allows us to model tons of different outcomes to find the optimal fit. We're then bringing all of those calculations together in a hidden layer, and then we're calculating one final prediction in our output layer to give us an overall prediction. By using this approach, we can model highly complex cases that we would not be able to capture in one simple model. So if we pull back the microscope now, we can see how each of these layers come together. And this is our neural network. Each node takes in a set of inputs, such as the features that we have listed here, applies weights to them in the hidden layer, and then makes a final prediction in the output layer. In the deep learning world, there are some neural networks that have millions of neurons and many, many hidden layers, which is why it's called deep. Also, one final word on deep learning. In this series, I'm using simple examples and skipping over a few technical concerns in order to keep this brief, but it's important to understand the main concepts. Deep learning uses neural networks that are modeled after the human brain in order to solve complex machine learning problems. Neural networks are made up of neurons, each which takes in a set of inputs, assigns weights, and generates an output. These neurons get arranged in layers which allow a neural network to figure out complicated problems that couldn't have been solved by simple equations alone. And lastly, having a good governance process is really critical here as we identify the right data for our model, extract relevant features, and establish a common understanding of how the data will be used to solve our business problem. So we've come to the end of part 2, and we've covered a lot of ground in this video. How algorithms train themselves, linear regression, gradient descent, neurons and neural networks. Hopefully this gave you a sense of how machine learning and deep learning work. As we've said throughout this series, the role that data plays and a strong data governance model to stand behind it cannot be overstated when it comes to artificial intelligence. In our next video, we'll focus primarily on that subject and talk about how data governance and big data will evolve and impact an AI-driven world.